Before beginning the discussion on AOA and its effect on airfoils, first consider the terms chord and center of pressure, or CP. As stated, the chord of an airfoil or wing section is an imaginary straight line that passes through the section from the leading edge to the trailing edge. The chord line provides one side of an angle that ultimately forms the angle of attack. The other side of the angle is formed by a line indicating the direction of the relative airstream. Thus, the angle of attack, or AOA, is defined as the angle between the chord line of the wing and the direction of the relative wind. This is not to be confused with the angle of incidence, which is the angle between the chord line of the wing and the longitudinal axis of the aircraft. On each part of an airfoil or wing surface, a small force is present. This force is of a different magnitude and direction from any forces acting on other areas forward or rearward from this point. It is possible to add all of these small forces. That sum is called the resultant force or lift. This resultant force has magnitude, direction, and location, and can be represented as a vector. The point of intersection of the resultant force line with the chord line of the airfoil is called the center of pressure, or CP. The CP moves along the airfoil chord as the angle of attack, or AOA, changes. Throughout most of the flight range, the CP moves forward with increasing AOA and rearward as the AOA decreases. The AOA changes as the aircraft's attitude changes. Since the AOA has a great deal to do with determining lift, it is given primary consideration when designing airfoils. In a properly designed airfoil, the lift increases as the AOA is increased. When the AOA is increased gradually toward a positive AOA, the lift component increases rapidly up to a certain point and then suddenly begins to drop off. During this action, the drag component increases slowly at first, then rapidly as lift begins to drop off. When the AOA increases to the angle of maximum lift, the burble point is reached. This is known as the critical angle. When the critical angle is reached, the air ceases to flow smoothly over the top surface of the airfoil and begins to burble or eddy. This means that air breaks away from the upper camber line of the wing. What was formerly the area of decreased pressure is now filled by this burbling air. When this occurs, the amount of lift drops and drag becomes excessive. The force of gravity exerts itself and the nose of the aircraft drops. This is a stall. Thus, the burble point is the stalling angle. As previously seen, the distribution of the pressure forces over the airfoil varies with the AOA. The application of the resultant force, or CP, varies correspondingly. As this angle increases, the CP moves forward. As the angle decreases, the CP moves back. The unstable travel of the CP is characteristic of almost all airfoils. The efficiency of a wing is measured in terms of the lift-to-drag ratio, or LD. This ratio varies with the AOA but reaches a definite maximum value for a particular AOA. At this angle, the wing has reached its maximum efficiency. The shape of the airfoil is the factor that determines the AOA at which the wing is most efficient. It also determines the degree of efficiency. Research has shown that the most efficient airfoils for general use have the maximum thickness occurring about 1/3 of the way back from the leading edge of the wing.